Okay, so let's continue to look at the binomial CDF and binomial PDF functions. All right, so let's take a look at question B. So what's the probability that 14 or more of the 22 participants would prefer the last Hershey Kiss that they tried? So once again, notice that now if you do this at the very beginning of the problem, you state the what x equals the number of participants who prefer the last kiss, and then the binomial distribution, we have 22 trials with a probability of success of 0.2. If you do that at the top of the question, you don't need to do it for every single solitary question. So I would just get in the habit of putting that at the top of the question you're answering so that you know that you're not missing points or you don't have to do it like a second time. In this case, we want to find the probability that x is greater than or equal to 14. If you need to, write out 0 through 14, cross out what you don't want. In this case, I don't want 0 through 13, I just want 14 through 22. So basically what this probability statement is telling us, probability that x is greater than or equal to 14, 100% that 0 through 14 minus what we crossed out 0 through 13, because 100% minus 0 through 13 is going to give us 14 through 22 left, okay? And this is what it looked like on your graphing calculator. 1 minus binomial CDF, 22.2, and then 13. Gives you the probability of 0.0001. And then just make sure that you answer the question in context. You can take a minute and read that to see what it should look like. Okay, so now let's take a look at the mean and standard deviation of a binomial distribution. So we've been doing this. We took a look at normal distribution. We always describe the center and spread by the mean and standard deviation. We took a look at random variables in the last section, the mean and standard deviation of the random variables. So binomial distribution is also going to have a mean and standard deviation so that we can describe the center and the spread of a binomial distribution. So we describe the probability distribution of a random variable just like any other distribution. So remember, a distribution is just taking your values and your probabilities and plotting them on a histogram or a dot plot just to see how the values are distributed. So let's consider the probability distribution of x, the number of children with type O blood in a family with 5 children. All right, so this was like our probability distribution that we talked about in the previous section. 0 children, 1, 2, 3, 4, 5 having a type O blood. Here's the probabilities. Remember, our histogram is the number of children, and then the height is the probability of each. Okay, since we are looking at a histogram, we can describe the center, the shape, and the spread. So the shape of the distribution is slightly skewed to the right. We're more likely to have 0, 1, or 2 children with type O blood than a larger value. The center, since it's skewed, we're going to use the median. This median of the type 1 blood is 1. And based on our formula for the mean, we could find out what the mean was. However, the median's more likely to be a good representation since it's skewed. Okay, so you're going to add 0 times 1 plus 1 times this plus 2 times this plus 3 times this plus 4 times this plus 5 times your probability. Add all those up to get the mean. Okay, and then the variance of x is, remember, we're going to take 0 minus the mean of 2.37 minus the mean of 1.25, okay, square that, multiply it by the probability, and keep doing that. 1 minus the mean of 1.25, square it, multiply the probability of that occurring. So remember, to get the standard deviation, we have to find the variance first, okay? Take the square root of it to find the standard deviation of 0.968. All right, so what exactly are the mean and standard deviation of a binomial distribution? So we did it this way by going through and doing all the calculations that we did with our random variables from the previous section, but we want to know, is there basically an easier way to find the mean and standard deviation of a binomial distribution? So if a count x has a binomial distribution with a certain number of trials, the mean of the distribution is the number of trials you have times the probability of successes. The standard deviation of a binomial distribution is the number of trials times the probability of success times the probability of failures, and you take the square root of that. So doing the calculations from the previous page can be long and tedious. They can take a long time. However, these two calculations are very easy to do and calculate to find in the mean, the standard deviation of a binomial distribution. I'm not going to go through and show you where these came from because they are often difficult to prove. They could be a pretty long proof of where these came from, but you don't need to worry about that. Just know that this is how you find the mean and standard deviation of a binomial random variable. Okay? Now, just keep in mind these formulas only work for binomial distributions. They're not used for any other distributions. And the question you might ask is this on the AP Stats formula sheet? Yay, it is on the formula sheet. You just have to recognize the fact that they are from the binomial distribution. So you'll have to A, recognize that you have a binomial distribution, and B, recognize what these formulas are. And then if you're asked to find the mean and standard deviation of a binomial distribution, you will just have to show the numbers plugged into the formula. But it's a pretty quick plug-in. All right, so let's take a look at our roulette example again. Remember, we're still having 10 spins of the roulette roll, 10 spins of the roulette wheel, and we're letting X be the number of, in the next 10 spins, X is the number of spins that land on black. So we're going to calculate and interpret the mean and standard deviation of X. Now, we have to recognize that this is a binomial situation, and this is oftentimes what students miss on the AP exam, is that they'll fail to recognize that this is a binomial distribution and not use the correct formula to find that mean and standard deviation. So we knew X was a binomial random variable. Like I said, you could just write B, N is 10, P is 8 out of 38. Let's use the formulas that we have to find the mean and standard deviation. So the mean is N, our number of successes, or sorry, number of trials, which is N, times the probability of success, or landing on black, is 18 out of 38. That gives us our mean. What would the interpretation be? We'd expect 4.736 rolls of the roulette wheel to land on black, okay? 4.6, if we were to do this many times, we would expect 4.736 rolls to land on black when we spin it 8 times, okay? Now keep in mind though, please don't round this. I know that you can't land on 4.736, like you're either going to land on 4 or 5, but please don't round it because it's changing the probability if you do round it. All right, so show the plugins for the standard deviation. 10 trials, success, failures. Make sure then you take the square root is 1.868. Now, same thing with the standard deviation. If we were to do this over and over again, specifically with 10 spins of the roulette wheel, the number of times the wheel will land on black would differ from the mean by about 1.868. Once again, please do not round this. Okay? All right, so let's take a look at a couple of other questions still dealing with our roulette roll. How often will the number of spins that land on black be within one standard deviation of the mean, and why? All right, so let's think about how we can do this. If it's helpful to draw a curve, go ahead and draw a curve, label the mean, label the standard deviation. We want to know how often will the number of spins that land on black be within one standard deviation of the mean. Now keep in mind, if we're going to draw this within one standard deviation of the mean, remember you have 34% above and 34% below from the empirical rule. That tells us that about 68% of the time they're going to land within one standard deviation of the mean. So if n is large enough for the binomial, if n is large enough, the binomial distribution will look like a normal distribution. And remember the empirical rule, about 68% of the data fall within one standard deviation of the mean. And we're going to go over this in a minute, how the normal distribution is similar to the binomial distribution. Okay, so the question is going to be, since we sort of use that normal distribution rule to sort of estimate this probability with a binomial distribution, how do we know if a binomial distribution sort of follows the same rules as a normal distribution? Now, the binomial distributions are important in statistics when we want to make inferences, okay, that means we're making predictions, about the proportion of successes within a population. Now, almost all real-world sampling, such as taking a simple random sample from a population, is done without replacement. So remember we said in the previous couple of slides, it's not really a binomial situation if it's done without replacement because the probability of success is changing each time. However, keep in mind that sampling without replacement does lead to a violation of the independence condition. But we want to know, is there a way around that? So when the population is so large, much larger than the sample, a count of successes in a simple random sample of size n has approximately the binomial distribution with n equal to the sample size and p equal to the proportion of successes in the population. All right, so that might have been kind of confusing. What that really means is if your population is large enough, okay, then as you sample without replacement, the denominator is changing, but not changing enough so that it's going to change the probabilities by a significant amount. So think about it. If you have a sample of size 10 and you sample without replacement, you take one out, you only have 9 left. That's a pretty big change. Take one out, you only have 8 left. That's a pretty big change in your probability. But let's say you have 8,000 people in the population, you take one of them out, let's say your probability is 1 out of 8,000, that's not going to be much different than 1 out of 7,999. So it's not quite independent, but it's almost independent because it's not changing the probability that much. So then the question is, how do we know how much bigger the population has to be? So if you're taking a simple random sample of size n from a population of size big N, we can say that it's binomially distributed if the population is 10 times the sample size. So this n, this small n and 1 over 10 to the big N is just saying if I take little n, multiply it by 10, it should be less than or equal to the normal, the population. So the sample has to be the population has to be at least 10 times the sample size. Okay, because what that does is that allows us to say, hey, wait a second, if the population is 10 times the sample size, then if I'm sampling without replacement, it's not changing my denominator that much, and I can still say that it's independent. So this is called the 10% condition, and you're going to see this throughout basically like the rest of the course. So get used to this 10% condition. And it's the reason that we use the 10% condition is because almost real world sampling is done without replacement. So like I said, get used to seeing this. We're going to be working with this. This does not mean that we want a small sample. It doesn't mean that our sample is small. It just means that we want our sample size to be less than or equal to 10% of the population. So basically the population has to be more than 10 times the sample size because that is telling us that the probability of success is not changing even though I'm taking somebody out of the population. If it's not, then you cannot use the binomial distribution to make inferences. Okay? All right. So let's take a look at this one, and we call this situation almost binomial. So when the population is 10 times the sample size and we're sampling without replacement, we're saying that the population, when we're sampling without replacement, the probability is not changing enough. It's changing a little bit, so we can't say it's completely independent. We can say it's almost independent or almost binomial. So almost everybody has a drawer of miscellaneous batteries. Maybe you don't, I don't know. But let's suppose that your drawer contains 8 AAA batteries, but only 6 of them are good. You need to choose 4 of them for your graphing calculator. If you randomly select 4 batteries, what's the probability that all 4 will work? Okay. Now, why isn't the answer probability x is equal to 4, 0.3164? The actual probability is 0.2143. Okay, now why couldn't we use the binomial distribution to come up with that answer? Because in that case we're sampling without replacement. The selection of batteries is not independent, so we can ignore this problem if the sample we are selecting is less than 10% of the population. However, since we're taking 4 of the 8 batteries, that's 50% of the population. So it's not, we can't ignore the lack of independence. When the population is 10 times the sample size, so we could say, okay, well, it's not quite independent, but that's okay. That tells us why the binomial probability is so different from the actual probability. However, if we did 40 batteries, 4 out of the 40, okay, 4 times 10, is equal to 40, so we could say that we can sort of ignore the independence. But this right here was using the binomial distribution to find the probability of x is equal to 4. That's quite a bit. That's about 10% off. So you want to be careful with that situation. Okay. All right. So I would say go ahead. This is actually sort of interesting. So as n gets larger, something interesting happens to the shape of the binomial distribution. So notice n is 10, n is 20, n is 50. What do you notice about the distribution as n gets larger? So what I'd like you to do is go ahead and click on this applet and just play with the values of n and p, and I want you to take a look at what do you notice when n is large and p is small. What about an n is large and p is large? There's a tipping point with n and p that makes the binomial distribution look about normal.